Hey, Dr. Clark coming back at you with another differential equations video. This one we're looking at the non-homogeneous spring mass damper problem. Sometimes we call that a driven or a forced harmonic oscillators. Let's take a look. So the first thing is, we're talking about non-homogeneous spring mass damper problem. That means we're taking our standard second order constant coefficient linear differential equation. But we've got right-hand side forcing term now. That's an external force on the system. We often call that driven motion. The spring mass problem is being driven by some other external force. You can solve these by finding the homogeneous solution and then finding a particular solution that incorporates that forcing term and then using superposition to add those two together. You should have seen that already in an earlier section. And we're going to be using that throughout this lesson. So what we're going to do is we're going to play around with different kinds of external forcing, and in particular, we're going to look at sinusoidal forcing. So if you imagine yourself, you've got a spring mass problem, and that mass is sort of oscillating left to right, left to right, left to right. It'll probably, if there's friction, which there would be in a real situation, settle down to zero. But what would happen if you had strapped onto that mass a little fan, and the fan could either blow it to the right or blow it to the left? And you could imagine the fan sort of blowing right and then left and then right and then left and then right and then left. Kind of like a forcing term, like a cosine function that sometimes blows one way, sometimes goes the other way, so positive, then negative, then positive, then negative. It would make sense that you might be able to get that spring mass to continually oscillate if you forced it with a cosine function. All right, and so what we're going to do is we're going to do an example where you see that happening. So we got a spring mass damper, mass is 1 kilogram, damper coefficient is 2, spring constant is 2, external force is 3 cosine. And they want us to find the general solution. And then note, are there any transient terms? Are there any steady state terms? Does anything decay to zero over time? And does anything persist as a response to the given external force? And what we should see is these homogeneous terms are transient and the steady state terms coming from the particular solution persist. So if this was our differential equation that we're trying to solve, step one would be finding the homogeneous solution. So we take our homogeneous differential equation, we write the characteristic equation, we find the roots. In this case, they're complex, which makes sense because we got a friction term there. But the friction is relatively weak compared to the spring. And so you get C1 e to the negative t cosine, C2 e to the negative t sine. That's that sort of oscillating decay solution that we've seen when we have underdamped harmonic oscillators. So that's the homogeneous solution right there. Now let's find the particular solution. So again, because the forcing term is a cosine, we pick our particular solution to be a cosine and its derivatives. Remember, the key with that particular solution is pick something that looks like the forcing term and its derivatives. In this case, the forcing term is a cosine of 4t, so we pick cosine of 4t. The derivative of that would be a sine of 4t, and we put a and b because we don't know exactly what numbers we need. We take the first derivative, we take the second derivative, and then we put the second derivative in here. We take the first derivative, put it in here. We take the function, we put it in here, and we see, can we get that to equal cosine of 4t? If we pick a and b correctly, we will be able to. So here's x double prime plus 2x prime plus 2x equals 3 cosine of 4t. And we're going to consolidate the cosine terms, consolidate the sine terms. These are all of the coefficients on the cosine terms. These are all the coefficients on the sine terms. And on the right-hand side, we have the 3 cosine of 4t. So you'll notice in green, I'm saying we've got cosines right here. Here's a cosine, here's a cosine. So there's 3 cosines on the right-hand side, and there are negative 14a plus 8b cosines on the left-hand side. So the number of cosines on the left matches the number of cosines on the right, and that gives you an equation. If we look at the right-hand side, there's no sine functions, but on the left-hand side there are. And so on the right-hand side, there's 0 sine functions, but on the left there are negative 14b minus 8a sine functions here. That's 2 equations and 2 unknowns, and hopefully you learned how to solve problems like that in high school. You can put it in Wolfram alpha, you can make a system and solve. If you do it correctly, you'll get A to be negative 21 over 130 and B to be 60 over 65, and that gives you your particular solution is negative 21 over 130 cosine of 4t plus 6 over 65 sine of 4t. Step 3, we write the general solution by summing the particular and the homogeneous using superposition because we've got a linear differential equation. Here's the homogeneous, here's the particular. And what I want to point out here is that the homogeneous part of the solution is transient. We've got these decaying exponentials here. Everything in green is going to go to 0. The response to the forcing term from the particular solution is going to remain over time. And so when we graph this, let me open up Desmos here and just show you the graph. This is what the graph looks like of, here I've got the homogeneous solution, here I've got the particular solution added together. It doesn't matter what the initial conditions are on C1 and C2. I can affect the initial conditions, yes, but eventually these transient terms go away and I'm left with just a cosine of 4x or a cosine of 4t, sine of 4t combination. And so this is called the steady state response to the forcing term. And these transient terms transition us from the initial conditions to the long-term behavior. Like so. And so here's the graph you can see again with the homogeneous solution and the particular solution together. All right, so that one was with a damped harmonic oscillator with forcing term. Now the next thing we want to do is look at another damped harmonic oscillator, this time with a tuned sinusoidal forcing. And what I mean by tunable is the frequency here is controllable by me. I can pick any frequency I want for that number A. And I want to solve this differential equation with A being any number. Well, if we go back to this earlier problem, you see this thing, there was a bunch of work that went into solving this thing. Imagine redoing this where instead you have an A instead of a 4 and an A instead of a 4. You could get the values of A and B in terms of little a. And that's what I've done right here. If you knew what A was, then the A, big A here, would always be this thing, and big B would always be this thing, depending on what A is. And now I want to see what happens as we tune that A. Okay, as we tune the A, so I've plugged in that homogeneous solution, same as before. The particular solution depends on A. I can again mess around with the initial conditions, but it doesn't really matter what I do with the initial conditions. Eventually, those terms decay away because they're transient, and we end up in the steady state response. Now, what happens to the steady state response as I try different frequencies? You'll see that as we pick higher and higher frequencies, the amplitude of the oscillation seems to decrease. And that's because that A shows up in the denominator as a fourth power, and so you end up with those things. As A increases, the amplitude of the sine and cosine shrinks. And what happens if A is 1? That seems to be when it's about the biggest. In terms of the height there, you see that when A is equal to 1, I'm getting my, I'm getting these amplitudes here to be basically as high as I can get them. And what's going on there is when A is equal to 1, the forcing term, the tune frequency, is similar to that frequency on the homogeneous term. And it's sort of like you've tuned your forcing term to be as similar to the homogeneous solution as possible. And so it's almost like that spring wants to oscillate with a frequency of 1. And so if you force it at a frequency of 1, you're sort of matching that frequency in kind of an interesting way. But in the end, because you've got the friction, it doesn't really matter what it is. You just get some steady state response, which is at the same frequency as the forcing term A. All right. So that's what happens as A changes. You get different behaviors. Now, the next thing I want to do is play around with an undamped harmonic oscillator. So look at the differential equation. There's no Bx prime, so there's no friction. Now, if there's no friction in this system, then the homogeneous solution is going to become pure sine and cosine right here. So x double prime plus 4x, if you think about the characteristic equation, is s squared plus 4. That's going to have roots plus and minus 2i, and so you're going to get cosine of t, 2t, and sine of 2t. That's your homogeneous right there. Again, we can do the same thing we did before. Take that cosine of at as the forcing term, put it on right-hand side, and then solve the particular solution for any number a on right-hand side, and you get this. It depends on a, but you always get 3 over 4 minus a squared cosine of at. Okay, so this will be the general solution for a undamped harmonic oscillator that's forced at a tunable 3 cosine of at. Now, let's take a look at Desmos here. So I've put in that homogeneous solution and the particular solution together, and I can try different initial conditions. If I get different initial conditions, that will change the homogeneous solution. Now the question is, what happens as I play that tunable frequency? Because now I'm combining these persistent sine and cosines, because there's no friction, with a tunable frequency. And here it looks like we kind of just get almost like a normal sine or cosine function. But watch what happens as I bring that A down closer and closer to 2, which is the natural frequency of the undamped system. This here is called beating. All right? So that behavior is called beating, and that's happening because the homogeneous frequency is 2. The particular solution has a frequency of 2.3 here. And if you think about, let me even make it even closer, 2.1. If you think about how would two sine and cosine functions add together, well, if you had a sine function with a frequency of 2 and a sine function with a frequency of 2.1, well, they're going to sort of be in phase and in phase and in phase and in phase and in phase for a while. They're going to both be up and then both be down and then both be up. And that means those waves are going to add constructively. But eventually, because the frequencies aren't exactly the same, eventually they'll become out of phase, and you'll get one positive and one negative and then one positive and one negative, and they're going to add destructively. So you can see here, those sine and cosines are adding constructively, and then they're adding destructively. And so you get this beat, which is related to how close the frequency is, 2.2 versus 2. The farther away the frequencies are, the shorter that beat is. The closer they are, the longer that beat is. Now, if the frequencies actually match, what happens to the denominator 4 minus a squared if a is equal to 2? Well, 4 minus 4 is 0. You just divided by 0. And now the solution disappeared. So what really happened there? Well, remember, this particular solution depended on A, the frequency of the forcing term. If A is equal to 2, you divide it by 0, this goes away. It doesn't exist anymore. And that's what happens when you have a forcing term that matches the frequency of the homogeneous. Remember what we did there? We slap a t on there. So the solution, if a is equal to 2, should actually be like a t cosine of at, not just a cosine of at with some constant on it. So that's what's going on there. We cannot plug in a equals 2. This solution only works when a is not equal to 2. So if a is equal to 2 and we force it at 2 cosine of 2t and the natural frequency is that, this here doesn't exist. We need to do something else. We're going to call that resonance. It's like the beats in this. It would be almost like if the beat continued to, because they never got out of phase, it would just add constructively forever, and it would be almost like this beat just going on up and up and up and up and up, down and down and down and down forever without ever going back to destructive. If you do the math and you solve that, what's going to happen for a 3 cosine of 2t, you can guess the particular solution as a t cosine plus a t sine, and it ends up being this is your particular solution, 3/4 t sine of 2t. That's what you get in your particular solution. And if we graph that one, that's right here. Here's that 3/4 x sine of 2x. You'll notice that that solution just grows forever, right? It never stops growing. The forcing term is never out of phase with the natural frequency, and so the solution just as a t cosine of 2t or a t sine of 2t just grows forever. That's called resonance, okay? If we go back here, we called this one here, we called this one beating because it had that sort of in phase, out of phase, in phase, out of phase behavior where they kind of like got these beats in it. This one we call resonance, where it's never out of phase and it just increases forever. So as a summary of all the things we've seen here, if you have a damped harmonic oscillator with forcing, that's that differential equation. If you have an undamped, that's that equation with forcing. If you assume the forcing term is sinusoidal, either a cosine or a sine, doesn't really matter which one. If the differential equation is undamped and the frequency of the forcing term matches the natural frequency, then you get resonance. That's when you get that t sine of 2t showing up. If it's undamped, so again, no friction, and the frequency of the forcing term is close to the natural frequency, then you get beating, where the solution kind of has these little humps of like increasing and then decreasing and then increasing and then decreasing. And finally, if you do have friction, then you won't get resonance or beating because the friction will always eat away some of the energy. Then it will turn out that the homogeneous will be transient and decay away, and the particular solution will just essentially persist as a steady state. And depending on the frequency, the amplitude of the steady state will change, but you'll always just get the steady state to match the frequency of the forcing term. So that's sort of the three things that can happen. Resonance and beating can only happen with an undamped system. If it's a damped system, you'll just get a steady state response that matches forcing term. Okay? What's really interesting is that LRC circuits are the same. So if you have an inductor, resistor, capacitor in a circuit, the differential equation is identical. Here I've written it for the charge Q in the capacitor, the second derivative of charge, the first derivative of charge, and the charge in the capacitor. Here's the external voltage from like a battery. It turns out that the circuit will satisfy the same properties. So the charge in the capacitor will sort of, imagine like a beating situation. It could like build up and then come down and then build up and then come down if your voltage was sinusoidal, like you're increasing the voltage and then decreasing the voltage and then increasing the voltage and then decreasing the voltage. You can sort of like build charge in the capacitor and then suck charge out of the capacitor and then build charge in the capacitor and then suck charge out of the capacitor, right? You can kind of get that capacitor to behave like an oscillator. If you have friction in the system, eventually just the charge will match the voltage, and if that's sinusoidal, then the charge will eventually be sinusoidal. So it's a little harder to understand how that's working with like the circuit, but what you can do is take your intuition from the spring mass problem, and it's the same differential equation, so it's the same behavior. All right, hopefully that's helping you see what kind of solutions are possible given different sort of forcing terms on right-hand side on those damped harmonic oscillators, and we will see you next time.